Hi everybody. In this session, we are going to discuss the concepts related to the first moment of area. And later in the second session, we'll be seeing the second moment of area, which is also known as the moment of inertia. So before moving on to moment of inertia, in this session, we'll be first seeing first moment of area, and then we'll see how centroid is derived from the first moment of area. Now, what is the first moment of area? Now, let's take that term. If you have a force F, you already know how to calculate the moment being created by the force F at a point which is at a distance of say d from the force or from the line of action of the force. So what will you do? In order to find the moment, you multiply the force with the distance d or the moment arm length d. Similarly, the moment of area, in order to find the moment of area or the term moment of area means it is the moment created by that area. So if you have an area, you multiply that area with the distance, then you get moment of area. And now here something more is there to the term, that's first moment of area. Why is it called the first moment of area? It's called the first moment of area because you are taking moment one time, and the first moment of area represents how the area or particle is distributed within the area. So let's consider an irregularly shaped body as shown in the figure, and this body is having an area capital A. Consider an axis XX below the body, and here we are considering a small area within our irregularly shaped body, two-dimensional body, and this area, small area, it is at a distance of y from x-axis. So in order to find the moment of this area, I can multiply y with dA. So y dA will give me the first moment of area. So as it's written here, the first moment of area represents the distribution of particle with area dA about x axis, and that's being obtained by multiplying y with dA. So distribution of particle with area dA about x axis is equal to y dA. Now, if I am considering my entire area to be formed by so many such small areas, here you can see a lot of red dots are here. It's not practical to cover the entire body using red dots, so but the actual meaning of this figure is that I'm considering my entire area to be formed by small areas, say dA1, dA2, dA3, etc. And each area is at a distance of, is having a distance from the x-axis, say y1, y2, y3, etc. Now, in order to find the distribution of total area about x-axis, you can integrate the previous equation. That is, if you have one area, the distribution of particle of that area is obtained by y dA, then the distribution of entire area being entire area about the axis can be obtained by integrating y dA. So distribution of total area about x-axis is integral y dA. Now, that being said, now the same area I am considering as a single area having area capital A represented by capital A, where area is represented by capital A, and I'm having same x-axis here. We are considering the same body as what we have considered previously. We are considering the same body. Now there is a point G being represented here. Now G represents the geometrical center of this area. This geometric center is also known as centroid. So G is at a distance of y bar from x axis. Okay. Now, if we are considering this figure, that is our entire area, to be a single area, if they consider this figure, then we can say the distribution of total area about x axis as y bar dA using our first moment of area equation. Now, comparing this with the previous equation that we obtained by disintegrating the entire area into number of elements, and here we have obtained the equation by considering the area as a single element. Now, the LHS of these two equations are same, so we are equating the RHS, and so we get integral y dA is equal to y bar into A. So by rearranging this equation, I can say y bar, which is the distance of the centroid from x axis, as integral y dA by A. So this equation is very important. Okay, and in some textbooks you will find this equation to be different, so I've represented it here. So y bar, as I've said, y bar is equal to um, y bar is equal to y dA. This is the equation that we have seen, and this equation can also be in some textbooks they represent the equation as y bar is equal to integral y dA by integral dA, where integral dA is A itself. So that's uh, that's how it's represented in some textbooks. So in order to avoid confusion, I'm saying this. And in some textbooks, if we are considering discrete areas that can be measured, here in our case it was not able to measure. If we are considering discrete areas that can be measured, and if we have the first area value and the distance of that area from x-axis, then we can sum integral y dA by sorry, not integral, summation of y dA by sigma y dA by sigma A, and that is equal to y1 a1 plus y2 a2 plus y3 a3 plus etc., or a1 plus a2 plus a3 plus etc. So this is also one representation. So when we are doing problems related to centroid, we will be using this particular equation. Okay. Okay, so let's move back to our equation. So that is y bar, that is integral y dA. For time being, we'll use this single equation itself. That is y bar is equal to, sorry, y bar is equal to integral y dA by A. Now, I'm drawing another axis, y-axis, perpendicular to x-axis. And let x bar be the distance of G from y-axis. So our G can be represented, our centroid can be represented using coordinates x bar, y bar, right? Okay. And we have already obtained the equation for y bar as y bar is equal to integral y dA by A. Similarly, in similar fashion, we can obtain the value of x bar as integral x dA by A. So, using the first moment of area, we have obtained the equations for x bar and y bar, which will give us the centroid of our area. So the coordinates of centroid of our area, of any area, can be found out using these two equations here. So these equations are very helpful, and these equations will be used to find the centroid in your in the problems. In the problems we will be using summation type of equation. That is what we have seen. That is y bar is equal to sigma y dA by sigma A. So in our problems we'll be using this equation, that is that is x bar is equal to summation of x a by summation of a, and y bar is equal to summation of y a by summation of a, or as you say, x bar is equal to sigma xa by sigma a, and y bar is equal to y sigma ya by sigma e. So that is our coordinates, or concept of centroid. Now let's see. Let's have a quick glance through what we have learned. The first moment of area, that gives the distribution of particle about an axis. Here the axis is xx. So integral y dA says, that is our first moment of inertia. Integral y dA is our first moment of inertia, and it says how the particles of this body, or this two-dimensional body, or of this area, how these particles are being distributed about xx axis. So from that we have obtained the equation for our centroid, the coordinates for centroid, x bar and y bar. These equations are very important. Okay, thank you. And in our next session we'll be seeing the second moment of area. Okay, for time being I'm ending this video. Okay, see you in the next session.